Hi everyone, welcome back for the second part of the lesson on volumes of revolution, solids of revolution. So this time I'm going to have a look at a little GeoGebra that I prepared earlier. Now I know this looks terribly complicated, but if we take it step by step we should be able to see how you can create your own models in this type of environment. So I started by creating a slider which I call T, and I've set that to run from 0 to 2 pi. I then have a slider A and a slider B, both from 0 to 5, and these will represent the lower and the upper bound of my integral, of my function. Now I chose to use a function of x here, which was square root x plus 1. And by putting the function of x into this expression, if x is between a and b, so that's the values here, 1 at the moment, and 5, yes, a is 1, b is 5. So basically I'm setting the domain. If x is between 1 and 5, then the function applies, otherwise it doesn't draw anything. Now you can see here as I adjust my slider B back to say 3, then it's updating here on this next object and it's updating the picture here on my graph. Now I'll get to this one over here in a minute. I've then used the command surface, and this is a three-dimensional one. So surface requires a function, f. It requires an angle, which is this parameter t that I set up at the start, and it requires a rotation axis, so I've set to rotate about the x-axis. Now that's all you need to write. GeoGebra will take care of all of this fancy stuff for you. It's a parameterized equation. It takes care of all of that, which is lovely. So as I adjust the value of t and we look across here at the three-dimensional view, you'll start to see that if I look at there, then that's pretty much the same as my 2D view. There's my function. There's the red is the x-axis, green is the y-axis, and blue is the z-axis pointing straight towards us at the moment. And as I were to rotate this around, it literally rotates that curve. Probably get a better view if I did that in a sort of a perspective. So there we go. It might just press the play button and let it do it by itself. So it rotates around the x-axis according to this surface command under the control of parameter t. Isn't that lovely? And I'll just hit pause there once it's got a full rotation. Now this is the object that we want to find the volume of, this object here. And the important things that we need to know are this function, that f of x equals root x plus 1, the lower and upper bounds 1 and 3. So that's and that's x-axis. So let's go back to our notes and see if we can do that. If I'll just write those things down. F of x, in my case, I wrote root x plus 1. I have a lower and upper bound of 1 and 3, so that's my domain. Then I was rotating about the x-axis. So my formula for a volume of revolution, pi, by the integral of from a to b of y squared dx. Let's do this. Integral lower limit is 1, upper limit is 3. My function is x squared plus 1, which has to be squared. Let's multiply this through. Root x by root x would give me x. Then I would have 2, and I might put x to the half rather than root x, and then 1 by 1 is 1. And I'm still integrating with respect to x. I think I'm ready to take an integral now. So integral of x is x squared over 2. Now my next term, there's a coefficient of 2. Increase the power by 1, that's a power of 3 over 2 now, and divide by the new power of 3 over 2. And the integral of 1 is x, and my lower limit is 3, and lower limit is 1 and the upper limit is 3. Now we evaluate. So I will have 3 squared, that's 9 over 2. Now note on this one here that when I divide by 3 over 2, it's the same as multiplying by 2 over 3. So it's really 4 over 3, and then I would have 3 to the power of 3 over 2 plus 3. Now, all of that should have brackets, and now we subtract when we substitute the lower bound. 1 squared is 1, that's 1 over 2, plus, here we go again, 4 over 3, and it's 1 to the power of 3 over 2, plus 1 this time. Don't forget the square brackets because the factor of pi is still at the front. Now when we evaluate this, I'll let you do that, and it will come out to be in some unit of measurement cubed. It'll be a cubic unit of measurement. I'll let you finish that calculation. And how will you know whether you've got your calculation right? Well, let's just go back to GeoGebra for a moment. Did you notice that I've put in an extra little line down here at the bottom where I've defined a calculation called volume, and I've gone pi by the integral of, oh look, it's my function squared from the lower limit a to the upper limit b. This is a GeoGebra command to calculate that integral of whatever I give it to work with. And it seems to turn out to be 36.43 cubic units. So when you check, you're working back here. Where is it? Scroll down a bit, please. Oh, silly old OneNote, why are you doing this to me? And I thought it was going so well. There you go. For some reason it got funny on me. So when you finish this calculation, let's hope that it all works out nicely and you get 36.43. Okay, that's enough for now. Very short introduction, and I'd encourage you to look at this example that I've made here and try it out for yourself. We can change our upper and lower limits. We can change our amount of revolution. And importantly, we can get in here and change the function that we're using as well. Now I'm going a little bit longer than I wanted, but why not? I mean, if you're still watching, then you're probably interested enough to do this. Let's change my function here to, I don't know, why don't we go sine of x? Now, there's an interesting function. Sine of x is doing this, and there's my volume. It looks like a little hourglass. Isn't that nice? I could, of course, go sine of x plus 1, just to push my function up to here, and now it looks like some sort of a pointy hat that you could wear. And the possibilities are endless. You could do anything you liked with this, any function you want, and change your limits and check your homework basically by setting up your own worksheet that looks like this. Okay, now I've had enough of your time. Thanks for watching. See you next time.